Welcome back. In the first half of this lesson, we saw how to use repeated multiplication, laws of exponents, and the Taylor series to compute non-integer exponents. However, that was all limited to a base of e. What if we want to compute a different base raised to a non-integer exponent? In a different lesson, we tried the method of taking a very small root. In this case, we took the 1,000th root of 2 and then raised it to 3,761. This method is not very efficient, and it is prone to round-off error. That can be seen in the last line. We have only 3 digits of accuracy compared to the true value. So how about a Taylor series expansion? That worked well for e to the x, but for a different base b, the derivative has some scale factor a associated with it. This has cropped up before in previous lessons, but thus far we haven't found a good way of evaluating this constant. So the fact that it shows up in every term of the Taylor series is a bit problematic. That can be seen in the last line. Let's go back to e to the x then. This base is special because the scale factor a is equal to 1 exactly. That way our final polynomial for e to the x is much simpler. How can we use e to the x to compute a different base b to the x? That's where our change of base expression comes in handy. This was introduced in an earlier lesson, but today we are going to implement it. Any base can be changed to a different one. This is done by multiplying the exponent x by some constant c. So to express 2 to the x as e to some exponent, we can make the following substitutions. Eliminating x from both the left-hand side and right-hand side, our objective is to find some number c such that e to the c is equal to 2. A bit of trial and error can lead you to c equals 0.693. Plug that into the Taylor series. You should get 1.9997, which is quite close to the number 2. It turns out there is a more sophisticated way to find c than just guessing, but it will be a few more lessons down the road when we cover that. Here is the spreadsheet of that calculation, by the way. Go ahead and make your own. If you're feeling ambitious, try to find more digits of accuracy in c. That will make the number underlined in blue even closer to 2. Back to our change of base. Now we can just plug the numbers into our example. 2 to the x is equal to e to the c times x. 0.693 times 3.761 equals 2.606373. E to the 2.606 can be split up into the product of e squared and e to the 0.606. We already calculated e in a previous lesson, so there's no need to reinvent the wheel. E squared is underlined in orange. We'll have to plug 0.606 into the Taylor series. However, the series will converge faster if we divide that by 4. So we plug 0.151 into the Taylor series instead. Then we take that number and raise it to the 4th power. That's just using our laws of exponents to improve the computational efficiency. The spreadsheet for that Taylor series is shown here. As underlined in the rightmost column, notice that every digit matches the one in the row immediately above it. Furthermore, in the 4th column there are 14 zeros past the decimal. This is a promising, although not infallible, indication that our answer has converged to that many digits. Now we can just multiply those two numbers together, as seen here. The answer is seen in the last line. Compare our estimate of e to the 2.606 to the true value of 2 to the 3.761. The true value can be computed by punching the numbers directly into a scientific calculator. It looks like we only obtained 3 digits of accuracy. However, It should be remembered that our estimate of c only had 3 digits, 0.693. Had we found more digits in c, e to the c would have been closer to 2. That would have ultimately led to less round-off error in our final answer. There is a way to find more digits of c, but that will have to wait for another time. The main takeaway from this lesson is that we can evaluate any base b to a non-integer exponent. That is best done by changing the base to e and using the Taylor series. That concludes another lesson. I realize that I have thrown a lot of information at you, so take your time to digest it all, and please don't hesitate to post your questions in the comment section below. A discussion of these examples will benefit our understanding of exponential functions. If you enjoyed this video, please like it and share with a friend. Also, consider subscribing to my channel so you can get notifications of my new content. I appreciate your support and look forward to seeing you again.